This is Mission Laika, linear algebra in kinematics and aerodynamics. In this video, we will explore an application of eigenvalues and eigenvectors from linear algebra in aerospace engineering. The Cessna Citation 2 is in flight and will soon start descending. It has been cruising steadily so far, but now it has encountered some turbulence. Because of the turbulence, the plane starts shaking and the wings start to vibrate. But are there vibration frequencies that are dangerous for the structural integrity of the wings? To analyze this, we'll simplify the problem and model the aircraft once more as a mass-spring system. Both the wings and the body of the plane will be represented as masses. In reality, the wings will start to move up and down, but to be able to use masses and springs, we will assume that they actually move in a horizontal direction. This is not a problem for our model, since we are only interested in the vibration frequencies and not in the actual movement. The masses m1 and m3 represent the wings and m2 is the body of the airplane. Since both wings are equal, all the springs have the same stiffness k. The x-coordinates denote the displacement of the three parts with respect to their equilibrium position. Let's look at which forces are working on the three different masses. Now, to keep things simple, we will not look at gravitational forces or any damping. We will focus on the forces generated by the springs. Which forces act on the fuselage, or mass m2? Both the left wing and the fuselage can stretch the left spring. The total amount the spring is being stretched is therefore x2 minus x1. The force exerted by the left spring on mass m2 is proportional to its stretch. Using a similar reasoning, we find that the force generated on the fuselage by the right spring is equal to stiffness multiplied by the total stretch of that spring. No extra minus sign here, because when the spring is stretched, the fuselage is pulled to the right or the positive direction. What are the forces acting on the wings? First, we will look at the left wing. We already established that the left spring generates a force on the fuselage equal to minus k times x2 minus x1. Since the left spring is attached to the fuselage and the left wing, it of course generates the same force on the left wing, but in the opposite direction. Therefore, we drop the minus sign. Something similar is true for the wing on the right. The force that the right spring exerts on the fuselage is equal to the force on the right wing and thus equal to minus k times x3 minus x2. Now that we have all the relevant forces, we can use Newton's laws to set up a system of differential equations. You probably remember that the force F equals the mass m multiplied by the acceleration term a. We will also need the fact that the acceleration of one of the bodies in our mass spring system is equal to the second derivative of its displacement x. Recall that we have put the three displacements in one vector x. The velocity vector contains all the derivatives of the displacements, and the acceleration vector the second derivatives. Since Newton's law applies to all three bodies in our system, we can set up an equation with the term m times acceleration on the one side and the sum of all forces that are working on that body on the other side. We have three bodies, so we end up with a system of three equations. Try to write this entire system of differential equations in its matrix vector form in the corresponding exercise. After that, we can proceed to investigate the vibrations of the wings of the plane.